I'm excited and honored to be here today to talk about my various experiences with NVIDIA Omniverse Create and how it's vastly improved my animation pipeline. I'm also going to be discussing part of my workflow in 3ds Max and all the amazing tools that offers as well, and how I use TyFlow to bring in all of my simulations into Omniverse for real-time rendering. Just a brief intro on who I am. My name is Edward McKevenue, and I'm a 3D generalist specializing in 3ds Max. I've worked in various parts of the animation industry over the past decade, dabbling in 3D animation for live events, to concerts, to working with various ad agencies on all types of projects. And a few years back, I also started a film production company where I was directly involved in managing and producing live action commercials alongside a really talented team of people. I currently run Ed Studios, and I handle creating all types of CG content for ad agencies and brands across the globe. So I just wanted to briefly touch upon the main tools and workflow I'll be addressing today, and show a few examples of some of the animations I built, and give you a behind-the-scenes look at how some of these shots were assembled together. A lot of my scenes are initially assembled in 3ds Max, either sourcing assets from 3D marketplaces or modeling and texturing them using 3ds Max's amazing native tools. After, I set up my simulation using TyFlow to complete my animations. And the last piece in the pipeline is NVIDIA Omniverse, where I combine all those assets together for final lighting and rendering. In case you're wondering, what is TyFlow? Well, if you haven't heard of TyFlow, it's a plugin for 3ds Max that replaces the native particle engine pFlow, and it was created by Tyson Ebeli. It adds many new amazing features and modifiers for creating all types of things from cloth, physics and fracture, ragdoll, VDBs, crowd, and all types of really cool particle simulations in a fast, multi-threaded way. As mentioned, for lighting and rendering my animations, I use NVIDIA Omniverse Create. And instead of over-explaining it, I just put together a little demo for you that kind of showcases some of the things I've been able to create with it. So that was a fun little animation I put together in a couple days, and I pulled together assets from TurboSquid and CG Trader and a few custom things, just to see how quickly I could assemble a sequence together. Now, in previous projects, I would have had to factor in a ton of extra time for rendering, and hope that I set up everything correctly the night before rendering scenes out. But by using a single 3080 Ti, I was able to render out everything, view, iterate all of my scenes incredibly fast. So let's jump in now and get a better look at how these scenes are actually created. This New York City animation was actually an old project from a very long time ago that never got finished. Because on my old render farm, it was taking roughly 2 hours per frame, which was painstakingly slow, as you can imagine. Omniverse changed things. When I started exploring its RTX path tracing and volumetric fog capabilities, I immediately thought of this project and was blown away by how fast I could bring in my TyFlow simulations, zoom around the scenes, find camera angles, and visualize 32 million polygons with a mist of light particles in real time. This is the original animation I was telling you about, where it was taking the 2 hours per frame. But I wanted to see how fast I could render it within Omniverse and see how I could improve upon things. In 3ds Max, I had two models set up, one of the city buildings and a second one of the various streets. Now, the reason why I needed these as separate objects is because the streets were used within a TyFlow simulation to contain the car particles to just the roads. Here you can see I'm using a simple sphere collider in order to generate particles only where the particles are colliding with that sphere object. Using a position object operator, we can position the particles to our selected street model and then use a surface test operator so that we can test where the particles are intersecting within the volume of our collider object. Next, once that's done, we add a particle shape operator so that we can change the shape of our particles to a simple sphere, which will be representing, in this case, the cars in our scene. Then by using a force operator, we can play around with the strength of the noise properties and adjust just how intensely the particles are going to try and glide around our network of streets. Finally, we add an object bind operator so that the car particles will in essence stick to the surface of the roads and will be contained to their boundaries. By tweaking the strength parameter, we can control just how fast our cars are moving along the roads and the amount of area that they ultimately cover. In this case, I'm happy with a strength of somewhere between 2 to 5, set as curl noise. Now, in order to visualize our trajectory paths, I'm going to add a spline pass operator, which will in essence add a sweep-like modifier to the splines. And then it will also make them renderable. I'm also going to lower the density of particles just a bit so that our street particles read on screen a little bit better. And that was pretty much all I had to do. For the last step, I simply added an export particles operator, and I exported my particle meshes as an Alembic file. This way, all of the animation is included and will work within Omniverse. Lastly, I then also exported the streets and the building models as FBX files. Now, jumping into Omniverse here, the first thing I did was I converted the street and the building meshes into USD. I then brought in my Alembic sequence of the TyFlow simulation. Now, when I scrub through the timeline, you can see my animation playing back as expected. So I'll adjust the timeline to match the animation range that I want, and I'll tweak the materials on the buildings just to darken things down a little bit. Lastly, I added an emissive light material onto the TyFlow sim object using one of the many material presets that ship with Omniverse. From here, by setting it to RTX path tracing, you can see the true beauty of real-time rendering within Omniverse. You get instantaneous feedback on your visuals, and you can add depth of field to your camera with physically accurate settings. But I finished things off by adding volumetric fog so that you could see that emissive light material from our particle simulation illuminating the fog and the buildings. Now, before Omniverse, with the samples and volumetric light setup I was using, it was taking, as I mentioned, 2 hours to see what the final result would look like. But with the speed of this workflow, it absolutely blew me away. What's so cool about this type of workflow is just how fast you can iterate on your camera angles, adjust your color correction, depth of field, without having to use a Z-depth pass, for instance, in After Effects, and then not also get discouraged by the render times determining the scope of your project. So here you can see a behind-the-scenes look on how the Omniverse project file I used on that final animation. You can just see how large the scene actually is and how fast and responsive everything remains. The bottleneck for me was actually the large Alembic file sizes, which ended up being 100 plus gigabytes. And it slowed me down only because I was reading those files from a network drive instead of a local SSD. So that's just something you want to keep in mind when you're working on it. The beautiful thing about Omniverse is how it combines content from all of your applications using connectors. And it's the final destination in your pipeline where all those assets can work together seamlessly. On this project, I was working with Unreal Engine and 3ds Max to create the visual effect of a building coming into existence in an abstract way. When you can see your building reflecting the environment with your materials and your shaders, it quickly inspires new ideas and helps you immensely when planning out your shots. It feels more like being a filmmaker on a real set where you can actually hold your eye up to a lens and see your final frame. So for this animation, I was really inspired by this pivot building method that was used in Unreal Engine to distort meshes with simple pivot rotation animations. And I wanted to see if I could recreate the same effect using TyFlow. Now, the way I built the 3D model was fairly simple. I had my structural layer built using a lattice modifier in 3ds Max, and then I had my floor layers, which were just boxes made in a 2x2 grid. So I played around with repeating and duplicating these layers, and that's how I completed all the floors. Once I was done, I just created the window layers of the building, once again using the boxes, and I adjusted the pivots so that they will align along the bottom part of the layer. Once I had one side completed, I simply duplicated the window walls across each side of the building, and that's how I was able to create all the pieces I needed for the TyFlow sim. So once I was done, in order to create the ripple effect, I used a torus object. And I animated the radius of the model to grow on once it collides with the building using a birth objects operator. I added my windows into the TyFlow simulation, and I used a custom properties operator to record/remember the original positions and rotations of my window objects. Then by using a surface test operator, we can test for proximity to the torus object. And then we can offset those positions and rotations and in essence lerp or interpolate back to that original home point over a set period of time. This gives us the appearance of the windows reacting to the impact and forces them to find their way back to the original home point. Here you can see the windows highlighted in blue being pushed to a new event and getting affected by the surface force operator. By experimenting with the strength of the operator, we can increase the intensity of how much those window particles are offset from the impact. In my case, I kept the strength of the force operator fairly low, as I wanted to keep that ripple effect very subtle. Once that was done, I duplicated my TyFlow sim 2 more times, and I simply added my lattice and floor grid objects to them so that they would also react to the torus collider. To export my simulation to Omniverse, I exported my floor lattice and my window particles to objects in my scene, and then I exported each one to its own FBX file, before finally converting these USD files into Omniverse. Now, I mainly played around with HDR lighting and material presets, and then moved into Unreal Engine to populate the rest of my scene. So I found this downtown 3D model on Unreal Engine Marketplace that I really wanted to use, as everything was nicely textured and ready to work with. Exporting these building assets was very easy. By using the Unreal Engine connector, all I had to do was right-click on an asset and then click Export to Omniverse. And then all of the shaders and the materials were then brought in and were ready to use. So jumping into my project file now in Omniverse, you can see all of the building textures, the lighting, the post-production settings are working in real time. It's really quick to fly around, set your camera positions, scrub through your animated TyFlow simulation, and even keyframe some movement on your cameras, for instance, for quickly building out your scenes. Lastly, I also brought in some car models from Unreal Engine and added a couple keyframes to give the scene more life. Once you're happy with your project, you can export your animations as image sequences and adjust the amount of samples and control just how much fidelity you want in your images. It's incredibly fast to iterate and to see your visual effects come to life. Part of the power of Omniverse is the paint extension. In traditional rendering pipelines, you have to add tools like V-Ray proxies or Forest Pack, etc., but you only ever see point cloud approximations or boxes as reference when planning out your 3D scenes. Omniverse takes things to the next level where you can paint your instances not as point cloud approximations, but in full detail, and you can see the final results in your viewport. You can then light your scene, and you can visualize millions of animated instances playing back in real time. So I was tasked on a recent project with creating a farm with wheat fields that had to show the various growth stages of wheat. So I animated a wheat plant in 3ds Max, and I used the morpher modifier to animate between the various phases of growth. I then exported that animation from 3ds Max as an Alembic file. Now what's cool about Omniverse is it has an extension called the paint extension, where you can add instances of animated geometry into your scene by either flooding or painting them onto objects. In my case, I wanted to animate my instances of the plants growing and also have them react to the wind. But I also needed to have a lot of control over the placement because the client wanted to show tractor lines and closely mimic the real process. So in order to do this, I made these large-scale objects in 3ds Max for the wheat rows so that when I flooded my wheat plants to the scene, they'd be generated in a very specific way. To generate large amounts of instances quickly, I used a cube that approximately matched the volume and dimensions of my wheat plant. And then I went into the raw USD properties to switch out the instances with a high poly version. Using this workflow, you can quickly test and iterate your instances, and when it generates, you can see literally millions of animated instances being displayed in real time, with virtually billions of polygons. You can also easily swap out your models as needed. So for example, with cylinders or whatever you want for a quick, non-destructive workflow. Early on, I explored using other methods like V-Ray proxies and Forest Pack, but at best you only get these boxes or these point clouds as reference, and it's a much slower process. In Omniverse, you see your entire scene displayed in full detail, complete with the animation, the materials, and lighting, and it's a completely different design experience. Afterwards, I wanted to see how I could harvest the wheat using the same workflow. So I built a simulation of a high poly wheat plant reacting to the wind in TyFlow, and I used the birth skeleton operator. This would allow me to build out the simulation so that I could have a 3D model of the harvester collide with the wheat plants and have them react in a realistic way. For the initial shots, I simply painted on the cubes and then I replaced them as before. But I generated 8 versions of the wheat plant reacting to the wind so that there'd be more variety in the timing of the animation. I love how fast you can add depth of field without having to worry about viewport approximations, or having to export a z-depth layer and add it in post-production, for instance. It makes such a huge difference to how the final shots come together, as all these little surprises can happen that sometimes inspire new ideas or direction for your shots. You can even add keyframes to rack focus, to change your aperture or your focal length as well. I love how you can see all the detail of your instances and light them as you would any other objects in your scene. So for the harvester scenes, the surrounding wheat plants were painted on as before, but this time I partitioned the wheat field so that there was a section in the middle of the field that was completely empty. Then I could place the simulation of the wheat plants colliding with the harvester and everything would blend nicely together. The trees in the background you see here were just a preset from the paint extension as well to fill in the background details. Once the scene was built, the real fun was being able to fly around, add my cameras, and set up my various shots. I could zoom up close to the wheat plant, or I could zoom way back and show the entire farm without having to worry about optimization or render time. So there's a ton of really cool things you can do with instances and this kind of workflow. So I wanted to experiment with digging simulations and see how I could solve the issue of subtracting volume from a mesh when something like an excavator takes a chunk out of the ground with its shovel. I ended up trying a few techniques before landing on the solution. My scene setup was fairly straightforward. I started by animating a 3D model of an excavator in 3ds Max, and then I passed the shovel part through an area of the textured ground mesh. For the first TyFlow simulation, I needed to create a voxel grid and simply remove particles wherever the shovel intersected. So I would need some kind of mesh with depth to it. Now to create that mesh, I isolated a region of the ground where the shovel was passing through so that I could extract it as a copy. This will be in essence the boundaries of the hole. Now with that extracted mesh, I could then use it to create an airtight volume using extrusion and a symmetry modifier. To minimize the amount of cubes needed within our volume for testing, I made sure to bring the bottommost layer of the vertices to just below where the claw of the excavator was passing through the ground. So now creating the TyFlow simulation, I could use that new mesh to birth voxels or particles within its volume. Think of it like packing a box with a bunch of small cubes. You can then adjust the density or the amount of boxes that are needed to fit within our selected object. Using a shape operator, we can change the shape of our particles to be whatever we want. In this case, I used a cube because I wanted to leave as little gaps as possible within the volume. By playing around with the density and scale, for instance, we can add more resolution or accuracy when creating the subtractive mesh. By using a surface S operator and selecting the shovel mesh, we can then delete any particles that collide with that shovel object. This is how I created the main subtractive mesh. By using a TyMesher operator, we can convert our voxel grid into a blob mesh. And to solve the problem of the blob mesh now rising past the original boundaries though, we can use a TyConform modifier to conform the mesh back to the original surface for a seamless match. For the very last step of this process, I also needed to create a density version of the mesh and then retopologize it. so that when I conformed it back down, I had more resolution to work with. So I made sure to preserve the boundaries by selecting only the interior vertices. And then I passed them up the modifier stack to a push modifier. Now, the only reason to push those vertices up is so that it prevents errors in the mesh when we end up conforming it back down later on. I then added another TyConform mesh on top, and I used ray casting to marry it back down to the original ground surface. I made sure to check off the UV settings because I wanted that original UV to pass to our ground mesh and transfer. I finally added the last TyConform modifier on top to remove any UV errors that were occurring, and finally a turbo smooth modifier so that I could smooth out the final mesh. This mesh was then ready to export as an Alembic file, which would save and record all the deformations and UVs on that geometry. For our second TyFlow simulation, I re-imported that exact same Alembic file that I just exported, and I used it as a collision reference so that I could add rocks and other debris interacting with that hole as it's being dug. I just used a birth intersection operator and used some preset pebbles and rocks as the shapes of the particles. Once I was done, I gave the particle shapes collision hulls, and I set up my collision targets so that when I added a gravity force, the rocks would then fall down to the ground as expected. And that's pretty much everything I needed to complete my actual simulation part of this project. I then needed to export all the pieces to NVIDIA Omniverse Create. So I exported the surrounding ground mesh and excavator as an FBX because there wasn't any deformations happening. And using FBX in this instance makes a lot more sense as the FBX will still save all the animation and UV data, but the file size will be a lot smaller than an Alembic file. So I only recommend using Alembic files when deformations are actually occurring. The third piece I needed was the hole mesh, which I exported as an Alembic file, leaving everything in the y-up coordinates. And finally, for the rocks, I used an export particles operator to export the rock simulation as an Alembic file as well, after leaving it in the y-up configuration just so that it was consistent across all of my file exports. So this is a behind-the-scenes look at the Omniverse project I ended up building. I converted the FBX files into USD, and then I simply dragged my Alembic files into the scene as well. My Alembic files were also fairly large for the scene. For example, in just the scene alone, the rock sim was 110 plus gigabytes. So it can really slow down your scene quite a bit, especially when you're scrubbing through your timeline to see the animation. Again, having an SSD drive definitely speeds things up as it helps Omniverse to read larger file sizes. After all of my elements were loaded in, I used an HDRI dome and a direct light to light my scene. Playing around with the direction of my light source, it makes it really quick to experiment. And even though Alembic files can be slow to load in, when frames are loaded, it's actually really still fast to zoom around and explore camera angle options for planning out the various shots. And it's quick to start snapping various sequences together. Lastly, I also used the paint extension with the included presets in this case, just to add in some additional rocks and trees, which is really handy for adding in lots of those extra little details. For this TyFlow simulation, I wanted to explore fracture simulations and dynamic wires, and see how that would look running in NVIDIA Omniverse. I set up the initial simulation using a few different parts. For the landscape, I animated a sphere moving along the road, and this would be the main piece that I used to drive my TyFlow road fracture simulation. And it would also be used to drive a volumetric selection with a push modifier on the ground surface in order to create a ripple or rolling wave type look. This allowed me to keep things fairly non-destructive, as I could simply reanimate the location of that sphere and the simulations would update accordingly. So if we take a quick look here, you can see I have my main sphere collider object, and in addition I also have a secondary sphere which will be used in TyFlow to trigger some additional TyFlow fracture events. So once that was set up, I was ready to move into simulating the various parts of my scene. Jumping into the first TyFlow simulation for the road fractures, I birthed the road into the sim, and I bound it to the desert mesh underneath. To trigger the fracture events, I simply used a surface test operator to test for the distance to our main sphere collider. As soon as the road mesh comes within a certain threshold distance to the sphere, it passes to the next event to be fractured into smaller pieces. I made sure to continually add object bind operators to each event so that our desert mesh rippled across the landscape. The fractured road particles would actually still stick to that surface. The smaller secondary sphere collider was trailing slightly behind the larger sphere object, and it was used to trigger the fourth TyFlow event, where the road trunks were fractured for a second time. And I also made sure to include the position and rotation operators as well in order to help to displace the particles and make the asphalt look like it was cracking as soon as the particles entered that event. To make the telephone poles rise and fall with the landscape, I selected all of my telephone pole objects in my scene, and then I added them into their own TyFlow sim. And then by using a simple object bind operator as well, I could have the telephone poles lock to the surface and react as expected. So to quickly go through it, I just used a birth objects operator to add them into my TyFlow sim. Then I binded them to the desert mesh using an object bind operator. And finally, I used an particles export operator to export all the particles out as scene objects, which would then bake that animation to the telephone pole objects and could be referenced by the wires later on in their own simulation. So that way the wires would also react as expected when the ground moved. Next, for the wires, I created these 2-point splines which would line up between the telephone poles. I then added them into their own TyFlow simulation using a birth spline operator, which births particles along the lengths of each spline. And then by using a particle bind operator, we can bind each of those spline particles to their adjacent neighbors so they act more like a rope. And then by adding a surface test operator, we can test for proximity to the other telephone poles and then disable and bind any particles that are within a certain threshold. That way, when the gravity force is applied, the spline particles then hang down like a rope with their endpoints still attached to the telephone poles. For exporting, I selected all the telephone poles and exported them as an FBX file. I then selected the desert mesh, and because it was deforming, I exported it as an Alembic file. Now for the telephone wires, I first went into the TyFlow simulation and I exported them as a TyCache spline scene object. And using the export particles operator, we can then add a sweep modifier on top in order to give the splines a wire radius. You can dial those values up or down to match your scene scale. Afterwards, I was then able to export the wires as an Alembic file. The last piece was the fractured road mesh. Now to export it, I went into TyFlow, and once again, using the export operator, export particles operator, I exported the particles as an Alembic mesh, making sure to leave it in the Y-up configuration again. And that was it. That was all I had to do to export all the pieces for my scene. So jumping into NVIDIA Omniverse Create once again, I converted my FBX files into USDs, and I dragged my Alembic files into my scene. Now, depending on your materials in 3ds Max, you sometimes have to rebuild your shaders in Omniverse. In my case, the road texture and sand materials were fairly simple, so I just added a simple Omni PBR material to my road, and I just selected my original diffuse texture. As I mentioned before, the only bottleneck for me has been working with large Alembic files, but for dialing in camera angles, depth of field, and lighting, everything still remains incredibly fast when iterating on your 3D designs. I was involved recently on a large commercial production for Ecobee that had several 3D scenes and a ton of VFX that had to be created for a new social campaign. Initially, it wasn't going to be rendered in Omniverse, but as the project evolved, it ended up being crucial to being able to meet the incredibly tight deadlines, especially with the number of revisions that had to be implemented. In total, for just the 3D portion in Omniverse Create, I ended up needing to render at least 16 4K plates for the final outputs, and this was in a very short period of time. At the start of the project, I had to model and create digital twins of the hero products for the campaign fairly quickly. And when I was creating the initial look dev during pre-production, this was especially important. The fact I was able to send updates on materials and lighting without having to worry about long render times on each revision helped immensely. They really wanted to accent the beveled edges of the glass of the Ares and the Artemis, which were the two hero products that were featured in the campaign. And as the storyboard showcased a lot of camera work following the silhouettes as light interacts with the metal and the glass features on the products, it helps immensely when you can animate your lights and you can see that glass reflecting directly in your viewport without having to constantly switch to another render frame for feedback. I also built the background Sykes, which needed to integrate their brand colors as 3D models. so that I wouldn't have to composite them back in afterwards in post. And it allowed for getting the real reflections of the environment and some of those blue and green color bounces back on the product as well. The client also really wanted to see the reflections of the real set on the surface of the product glass because the 3D footage had to match pretty closely with the live action versions of the product that were being filmed. So on set, I was able to grab 360-degree images, and I built my own HDRIs to match the original set. And I took rough measurements to recreate the set digitally in 3D for later use in transitioning to that table shot. Originally, the table shot was actually going to be live action, but it ended up making more sense for consistency to do this entirely in CG. It also made more sense to create a oneer, so to speak, in the animation setup and animate the lighting and set pieces to have direct transition to that living room set, instead of doing a hard cut and faking a transition in post. What was nice about this setup as well is that there's different storyboards requiring rendering the Ares and Artemis in the exact same scenario. So to avoid a mess of files with all the ongoing lighting, camera, material visions that were concurrently happening throughout the project, I used sublayers to be able to quickly switch between products, so both product animations always stayed consistent in revisions. That way, I could add or remove the white sensor, for instance. I could change the background site color or add products to the tabletop based on what the storyboard required. And what's really cool about sublayers is that they propagate across all of your project files. So for instance, if you change your USD file, it will be loaded in the same way across all your other project files that reference it. You just have to be careful about overwriting them, especially when removing objects in your scene that are controlled by that sublayer. But I love the modular aspect of this workflow as it allows for non-destructive revisions that keeps all your files and your project properly organized. Now, for the part of the project with the silhouette of the Earth transition for the Ecobee product, it originally was going to be rendered in 3ds Max, as I didn't know if it would be possible to get that specific look that the client was asking for out of Omniverse. Initially, it seemed like a pretty heavy compositing exercise, but after doing some small tests, I changed everything over to Omniverse Create. I love how it can handle multiple 16K textures of the Earth and clouds, and just how easily I can animate my lighting to extreme positions without any kind of lag. I never had to worry about guesswork or hoping multiple render outputs would connect together in post. I could just see everything in my viewport as the final output and make instantaneous design changes on the fly. Working with geospatial data was something I wanted to explore after seeing some really cool projects built in Houdini. It started with the challenge of how do you plot a point in 3D space using longitude and latitude data in 3ds Max. After doing some R&D, I created this project as a fun problem-solving exercise to see how I could use 3ds Max and an open data source to visualize 3D geospatial data in Omniverse. I was playing around with ideas and came across parking ticket infraction data for the city of Toronto. Now, there's a ton of really cool open data sources you can pull from, but I figured this would be a pretty good place to start. I thought it'd be fun to try and plot that data in 3ds Max and see what kind of animation I could create. For my limited experience, there was a lot of cleanup that actually had to happen, as that data was partitioned into multiple CSV files for each year. So I just focused on 2020 as a starting point. In total, there was 1.5 million records with street addresses and the fine totals. So I converted that data into a version that had node IDs and longitude and latitude data, which was created by using Geocodio in order to convert those street addresses to something I could plot later on. Fortunately, my brother is a data visualization expert, and he was able to help summarize the fine total per address and further help me with cleansing and organizing the data with Power BI. Lastly, I outputted everything into an OSM format for bringing into 3ds Max. I found a cool plugin called MapRoom, which uses OpenStreetMaps to draw in land masses, buildings, and streets using simple parameter configurations. So for instance, I could set my location to Toronto, and I could draw in an area of 20 square kilometers, and then even bring in the map textures from sources like Bing using various API keys. You could even bring in elevation data so that your landmass shows valleys or mountains, for example. Once I had my City of Toronto map loaded, I created a new OSM layer. And now what's cool about MapRoom is you can also bring in all kinds of OSM data, from street shapes to buildings, and even custom OSM data if you want, which is exactly what I used. So I loaded my custom OSM file, which was exported from Google Sheets, and it generated a bunch of these point helpers, which were defined by their longitude and latitude data, and it accurately plotted out all those points. I then wrote some Mac script to create a box tower for each parking infraction location, and have the height of that tower be determined by the quantity of parking fines that occurred at that exact location. It directly reads a CSV file, and it looks at the specific column as reference, and then animates it on the height of that box over a set period of time. That way I could visualize the parking areas in Toronto that had the most fines, where I'd be most likely to get a ticket if I went there. Once that was done, I added gradient UV mapping to all my box towers so that I could represent the intensity with the color gradient. By applying a shared UV map and rotating the gizmo, all I had to do was apply the same gradient material to all of my box towers, and everything was then ready to export into Omniverse Create. I exported all of the boxes as an FBX file because there weren't, again, any deformations in the mesh, so it helped cut down on the file size tremendously. Then once again, I simply converted that into a USD format within Omniverse, and everything was ready to go. Taking a look at the project file, you can now appreciate the scale at which you can work in real time. I purchased this 50 square kilometer 3D map of Toronto and overlaid some of the parking data on top. It really just is fun to fly around the scene and brainstorm ideas for the best way to animate a scene once it's built. In total, there was $70,507,332 in fines issued in 2020, and that was for 1.4 million tickets. So if you can, avoid 4001 Leslie Street, where over 5,340 tickets were issued. And this is North York General Hospital, by the way. It makes a lot of sense. Pricey $201,000 in tickets at that location alone. And the location which brought in the most revenue was 1 Brimley Road South, with a whopping total of $438,000. And it was 3,800 plus tickets. And this was actually located near the Scarborough Bluffs Park, for those who are familiar. Now, this project isn't finished yet, but I still wanted to share my workflow as there are some really cool things you can do using this method. Think about the possibilities when you don't have to worry about limitations, and you can finally create at the speed of creativity. These are just a couple bonus scenes I didn't have time to go over today, but I just wanted to share in case it inspires some ideas. We can use rigid body sims with some simple curl noise in TyFlow for something like this coin simulation. Or create a driving simulation using Craft, or even the car tool rig options directly available within Omniverse Create. I use TyFlow for the Jenga block pieces here, but Omniverse actually ships with its own super fast physics simulator, so it's even easier to do it that way, which means you would also get instant feedback in your viewport with the ability to record/save your favorite take of the day. For this simulation, I wanted to showcase particle deformation and figure out a fast way to use TyFlow to deform meshes. This is useful for additional effects in your driving simulations for things like snow, or for mud, or for even sand. You don't have to include particle simulations to get cool results. This animation, for instance, was built entirely in Omniverse, and all I did was add some simple camera movement and animated a single directional light source, and then snapped it all together using a few camera angles, and then rendered it out in 4K. There are lots of cool things you can do just bringing in the raw Alembic exports from TyFlow. I built this simulation fairly quickly and then used preset materials and two-directional lights within Omniverse to create heavy abstract particle renders. So I hope some of these techniques inspire new ideas. I have a ton of areas I'd love to explore still, combining the power of 3ds Max, TyFlow, and Omniverse. If you're interested in what I'm currently working on, here are just a couple of future projects in the works. Back when I was in elementary school, I loved creating stop-motion animations, and it's what actually inspired me to learn 3D animation in the first place. So I'm going to go back to my roots, and I'm going to see what I can create as a tribute to that style. This is just a quick test running in 3ds Max and V-Ray. I also created a short film called s.r.l in Unreal Engine, and I'm currently working on a new short film which will be built using 3ds Max and Omniverse. And I'm planning on seeing how I can really push the limits of my skill set to see what I can achieve. I'm also working on another larger project using 3ds Max and TyFlow, which you can see some of the R&D animations I created here. But each of these took roughly 14 hours to render each, so I'm going to be exploring translating these projects back into Omniverse and compare results as soon as the project's finished. For the last project I wanted to share, I built this MaxScript plugin that arranges selected objects into a grid array, kind of like a Greeble kit bash creator that creates procedural materials, complementary color schemes, and just makes really cool procedural art. So you can see when I click generate here, it just spits out random results. And there's a whole bunch of different variables to give a ton of different variety. So you can see these are just some of the results that I was able to create. But the next plan is to code this as an extension in Python and then share it with the Omniverse community to see what other artists are able to come up with. There are so many additional features I didn't have time to cover today, but I just wanted to give you a small sample of what's possible. All of these tools are absolutely amazing, and I highly encourage you to explore all that 3ds Max, TyFlow, and Omniverse has to offer. Just to note, on my YouTube channel Ed Studios, I have a bunch of long-form tutorials which explains these projects more in depth. So if you're looking for more information on how to create animation using this workflow, that's a great resource to check out as well. I just wanted to say a huge thank you to NVIDIA and for Autodesk for inviting me here today. If you have any question about today's presentation, I'd love to answer them. And just to mention briefly here, if you aren't watching the live version of this presentation today, you can always shoot me an email to contact@edstudios.ca, and I'd be happy to answer any questions you have. Thanks.